And so we are on the record. Okay, hello everybody. I'm happy that you're here. Now we can go through a few problems. Start with these two very simple questions, and then we will go to the third one, which is very similar to what you see in the third question of the second homework, and that problem is also from the slides. So if you don't have anything to say, I can continue. Good. All right. So the first problem from slide is that this is the function that you can see, I guess, on your screens is x minus 2 square minus x minus 2, y minus 2 plus 1/2 of y minus 2 square. So we want to minimize this function, and the initial point is given -5, 2, and you're supposed to have the step size of 0.1. Okay, so let's start by first, and I think the font size is good enough. If you cannot see, please let me know. Okay, so we start by defining the function. It is not that important to define the function, but I'm gonna do it. It's all right. So it is x minus 2, and please note that if you think that these stuff are very easy for you, I think these two questions are gonna be very easy. So please cope with us, because maybe some people need to have to start from easy question. So this is the function, as I guess you can see, and there shouldn't be any problem. The second important part that we need is to get the gradient. If I'm pretty sure that you all know that in gradient descent, we need to start from some point and then gradually get closer and closer to our optimum, which can be the maximum or minimum. It's up to the problem, but of course, one very important part is to get the gradient, which should be really easy. And I want to ask if anyone has any problem with getting the gradient of this function. Or let's do it the other way. Can anyone tell me what is the gradient of this function, please? I hear you. I hear some of you. I think some of you want to. I think some of you want to answer, but you're shy. Please try to be involved, because it's easy. It makes it easy for all of us. Oh, okay. Please talk, because if I go back, I will see this. I mean, I prefer you talk, but it is okay. So you're saying that 2 times x minus 2 minus 1. Okay, good. The thing is that when you see a multivariate function, and when you want to get to its optimum, then you have to be careful with all of the variables. And in this function, we have two variables, x and y. So we need to know where to go for both of these variables, both for both x and for both y. And this is actually what gradient, I mean, this is when we need the gradient. because gradient is going to tell us where to go for both of them, because gradient is a vector. Gradient is a vector and has one entry per variable. So if you want to optimize with respect to x and y, your gradient has an entry for x and an entry for y. So your gradient has to have trees. And I hope you don't mind me typing here, because I don't think it is going to take a short time. I have these ready, and if I see that it is gonna take a long time, I will. So I think it's not working. I think I have to. Okay, let me copy paste from what I have prepared before, because okay, but let me just okay. As I think you can see here, so the gradient consists of two parts. The first one is the derivative with respect to x, and the second one is the derivative with respect to y. What if our function had more? For example, I don't know, a capital M variables, then your gradient had if your function had capital M variables, then your gradient had capital M entries, just like this. So the derivative with respect to x is that, as I'm pretty sure that you all know, and the derivative with respect to y is that, because if you have a problem with getting the gradient, please let me know. But I think you all know how to get the gradient, get the derivative. So the whole gradient vector is this one, x and y. Does the order important? No, but you have to make sure that it is consistent all over the place. So here we have x first and then y second. All right, so let's implement this function. Well, get gradient. So for calculating the gradient, I guess the only thing that I know about my function, so the only thing that I need is x and y. So I will, sorry about that. I guess we all know what is going on. No, actually, I prefer this one. Okay, so I'm using NumPy, which is quite useful, and I suggest you learn how to use NumPy. We can just skip NumPy, but I prefer not to. So the gradient is, so first I initial the gradient, and then I will say that the gradient of 0 is equal to 2 times x minus 2 minus y minus 2, and then the gradient 1 is equal to minus x minus 2 plus y minus 2. If I let me make sure, just yeah, I think everything is fine. All right, so any question? Do you understand what is it, what it is, or do you have any problem, or do you have any problem? Good to go? Please show me
I have
some.
a question actually. When
Oh,
you're
good,
taking the
good, good.
when you're taking the partial derivative of y for the gradient at one, wouldn't the negative signs cancel out? Because like if you take the partial derivative, y turns to one, and then it's one minus two times the negative sign in the front. So wouldn't that be positive?
Okay, so first thing first, we know that we don't have this term in the partial derivative of y because it doesn't have any y. Okay, so x minus 2 the square is canceled. First thing first. Okay, so here I have 1y and then I have 1 minus 2. What is the, I mean, y here is positive, right? And I can just forget about this minus 2 because minus 2 times x minus 2 is also doesn't have any y in it, right? So the only, I mean, here the only term that I'm thinking about that concerns me is y times x minus 2. So its derivative is x minus 2, and it happens to be negative. So it is negative x minus 2.
Okay, that makes sense now.
Do you see what I'm saying? I mean, this is how I do it. I don't care about that negative sign, and all I see is x minus 2. So I put x minus 2, and then I add that negative.
So you just ignore the non-y term.
What? Ignore
You
what?
just the non-y term like in that expression.
Yes, 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 yes.
Okay.
Just, yeah, yeah. Just throw them out because they
Okay.
don't have one. And this is the part. This is the partial thing. Actually, this is what partial does. That it doesn't, I mean, in real world, let's say maybe x is a function of y, but in partial derivative we don't care,
Okay. Thank you.
right? So just throw them out. And and the for the last term you have 2 times 1/2, which is 1, and then 1 minus 2, and then the derivative of 1. Okay, let me just write a quick note here. So let me just write a very quick note here. That uh, 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 mm, let's just say that f of x, the power of 2, yeah, I think it should be clear. I mean, f of x, it is 2 f of x partial. Oh, I'm okay. Do you see this one? This is something like y minus 2 to the power of 2. So the thing is that you put the 2 and then you put y minus 2 because here y minus 2 is your function, is the f of x, and then you take the derivative of y minus 2, and the derivative of y minus 2 with respect to y is 1. So it is 2y minus 2, and it has a 1/2, so it is just y minus 2. Is it clear? So
Yeah.
great. So I read this one. Okay, so I guess the gradient function is also okay because yeah, it is 2x minus 2, it is y minus 2, and then it is a row. As you can see, it's a row with 2 columns. So okay, so we have our function and our gradient. What do we want next? This is what I prefer to do. I mean, I guess you're familiar with this concept of top-down and bottom-up coding. I always liked, I mean, I think top-down coding is easier, and I can tell you that it is easier for a TA to grade. So I guess if you're not 100%, you should start top-down because your grade is gonna be better. I mean, because I can see that you know what is going on, but you are not familiar with what you're not completely. I mean, but you're not 100% on details. So I recommend you go top down. And by top down, if you don't know what I'm saying, you will see. Uh, by top down, I mean that you start from the very main function that you have, and then you just put the coarse grain. I don't know if it makes sense or not, but you write your program coarse grain, and then you add details one after another. So this is what I'm going to do. Initial point is p dot array uh, minus 5 2, and then iterations. I hope that you don't mind me is having those. I hope you don't. Okay, so and then I want to apply. Uh, oh, and we first go with gradient descent, and then I add the project thing. Okay, so gradient descent with the initial point and with the iterations, and I get this one as x star y star as the final answer, right? So I want to have something like this. I want to apply a gradient descent, and I know my function. If you want to have the most general thing to write, you should pass the function here. But here we know the function, and we're working with a fixed function. So yeah, let's say that okay, I want to apply gradient descent with this initial point and with this number of iteration. So what is missing here? This gradient descent function. I don't have it. So let's implement it, and I will put it on top of it just to make sure that I'm going to. All right, so now I define this gradient descent. Make sure that these two are the same thing. No, okay, now they are. Initial point and iterations. What do I want to do here? This is how I usually do it. That I will say x and y is equal to initial point. And then what do we do? Okay, can someone please answer my question? What am I going to do? What am I supposed to do? Gradient descent function? Can someone please answer? No, no one. Okay, fine. Okay, so I have to implement. No, please talk because I have. Uh, yeah, that is exactly. So you're saying that xt is equal to xt minus 1 minus gamma times the gradient, which is completely correct. So I need to have my iteration. So I will say that for iteration in range of iterations. So I'm going to do this thing for that number of iterations that I have. So iteration in range of I prefer to always start my iterations from 1. So for iteration in iterations, I need to what am I supposed to do? I need to get the gradient. I need to get the gradient. Oh, come on. I need to get the gradient of my np dot array of x and y. What else do I need? Oh, I'm passing them. Okay, I'm passing them separately. So x and y. I get the gradient, which is the gradient is equal to that. And then what else do I want to do? I want to implement that one. So I will say that x is equal. Oh. And I think you remember that the gradient is a vector. So the gradient here has two entries. So the first entry, as we stated before, is corresponding to x. So x is equal to x minus gamma times gradient 0. And y is equal to y minus gamma times gradient 0. Correct, I think. But what is gamma? Let's.
Shouldn't you
We
correct
have.
it gradient 1 for y?
I didn't understand. Can you repeat it, Christian?
For y equals y minus gamma times grade, shouldn't it be gradient 1?
That is correct. My bad. That is correct. Good observation. Okay, thank you. So y is equal to. So as I said, we have 0 and 1. We have two entries for gradient. The first one is corresponding to x, and the second one is corresponding to y. So we need a 0 for x and y for y. And here we have a fixed gamma, which is 0.1. So what else do we need?
You got to move your r's around. For the x equals x minus gamma times.
Yeah, that is correct. That is the projected part. But I guess we should first implement the plane gradient descent, and then we will add the projected part. So for now, I think we are good. Does anyone have any idea what to do? What else should we do? I don't see anything. So let's go. Okay, so I have my function, I have my determinant, my gradient, then this function is okay. And I think that we should have this one, but of course error. So here gradient 1 out of bound for okay, so let's go see what is going on. Okay, as I don't know what is happening, I'm going with 0 0. Okay. Yes, of course. Okay. No, I don't worry about it. If I what was that?
Gamma times. You spelled it wrong. Just hit your A a
Really?
little early.
Oh, it's here. Right. It's not. Okay. X star is not defined. X star. This is X star. This is not X star. This is all the problem that you have. And okay, is it the correct answer? Who knows? But I know because I have it here. No, it is not. It's not the correct answer. It should be 2 2, something like that. Let me make sure that we have everything right. Oh, okay. I changed it. Okay. No. Let me do this for you to all see. This is my previous implementation that I prepared for today. And this is the get gradient, and it's here. I will compare this one to that thing so that don't waste too much time. Come on. Oh, I think I can do this. Yes. Good. Good gradient. So okay, what I can understand here is that this is pretty much the same. Initial point, iteration
Did
plus
diminishing gradient there.
1. Can you repeat?
You did diminishing gradient. You don't have a fixed gradient.
Oh, okay. I guess. No, I didn't understand. What did you say?
Look underneath gamma. Is this gamma equals 2 divided by 2 plus
No, this
iteration?
one is commented. No. This is commented. I mean, I was trying to do both, so this is not for us, and this project is also not for us yet. Right? No. Let me just. And this is the other function that I have. To me, everything look similar. This one is even important. This is 2 times x minus 2 minus 1. This is minus x to 2 minus 1. So it is, I'm passing this one, which is okay. I will switch to the previous code in a few minutes if I can find what is wrong. But I want to make sure that you all understand what I did. So if you have any question, please ask. And meanwhile, I'm searching for, see what am I doing wrong. This is the only thing that I can do, which is stupid. No, it should be something like 2.
Excuse me. Is that like? Are you sure that was like before the projection or like?
Yeah.
You got
I
the
mean,
numbers
look
after
at the
projection?
function. Yeah, no. Look at the function. The function is always positive, right? If you pay attention, the function is always positive. So the minimum should be in 2, which is 0. Right? Because okay, let's see this. Let's see this answer that we have. It is 0.2. It is 0.6 and 0.2, right? So if we put 0.2 and 0.6, we have something like 1.4 to the power of 2, and then we have 1.4, which is negative, and then we have yeah, we have something larger than, I don't know. Let's check it. Why am I doing this? Okay, so let's just say that f of print f of 0.6 and 0.2, right? And then print f of 2. Let's see which one is smaller. See, this one is 1, this one is 0. So yeah, we need to get to 2. This is the problem. Okay, so let me actually okay, switch, and then we will get back here to, what is that one? Wait a second. Oh, no. Okay. Okay, and I guess you're seeing this office hour October 8, right? Can you see this?
Yes.
Good. The function is the same, and the implementation of it is the same. So the gradient is the same. So the gx is this one, y is this one, and then we just return the gradient and just skip this project because I want to add it later. And then we have this gradient descent with the initial point and the iteration. So the initial point, the first one in x, the second one in y, and then gradient descent. Yeah, this is unfortunate that the other one doesn't work, because so if you run this one for only 100, let's go with 1,000. So the answer is very close to 0, actually 0, and this is almost 2. This is almost 2. Do you want, which part do you want me to explain more? Or was it fast? I don't know, how was it? But if it was too fast, if it was too trivial, please let me know. Please give me some feedback so that we can have a better session in the next part.
I thought this part was easy, at least.
Okay, good.
This part is fine.
So, pardon?
I said this part is fine.
Oh, okay, good. So, what about the projected gradient descent? In projected gradient descent, what we have is everything is exactly similar, but the only problem is that after redoing these updates, the x and y, so the whole point, might not be in the domain that we want it to be. So the only thing that we have to do is to, I mean, it's just one algorithm that that you're supposed to check whether this point is inside the domain that you want or it's not, and it is usually a convex set, but yeah, it doesn't matter now. So is it there or it's not? And if it is not, then you have to project it. And what does it mean to project it? It means to find the most similar point from that from your main domain. You have to find the most similar point to this one. What is the how can we measure similarity? We can use norm 2. We can this is just one thing that we can do. We can just use norm 2. So among all the points in the domain, we want to find which point is closest to the point that we are having here after updating. The idea of projection is just that. So what will we do? We add this function here. So we give it x and y, and then we want it to project x and y into our set, into our intended set, into our main domain. This is the only difference that a normal gradient descent has with a projected gradient descent. But what is going on in that function is important. So is it clear? I want it to be clear so that I can go to the projected function.
That's clear.
Okay, great. So we come here. In this very case, that we just want x to be smaller than 0 and we want y to be smaller or equal to 0, this is a very easy case. Why? Because the projection is quite easy to calculate. If x is greater than 0, then just put it equal to 0, and if y is greater than 0, then just put it equal to 0. But this is just this case. It might be more difficult. You might need to have an optimization problem to find the closest point in that set. So this is it. This is the function. This is the projected function. And one advantage of programming this way is that you don't have to change this function. This is just the very general thing, and you can always have this one here. And if you don't want to project it anywhere, I mean, if your main domain is just everywhere, you can just return x and y, and it works just the same. But but I mean, it is easier to handle the whole code here this way, because you can just come straightly to this function and just change the projection as you want it. So the global minimum is 2, 2, and I think this is going to be, wait a second. I'm waiting for a 0, 0. Okay, good. So and the answer is 0, 0 with this one, since I am forcing my point to be less and equal to 0 in both dimensions.
Question?
Go.
So could you explain setting those values equal to 0 and why we're doing that?
Exactly. Okay. Let me use something like this. Okay. So let's say that this is the best thing that I can draw. But okay, so let's just say that you want your this is where you want to be, right? This is where you want to be. So if you are here, if you're here, where is the projection? Where is the closest? I'm going to use all the colors. What is the projection of this point in this part? Can someone help me with that? Where is the projection?
It would go straight down, basically.
Exactly. It will go straight down. So the projection is Dun, dun. Here, right? So this is the projection of the purple one. If I want to project purple one into the red domain, it will be this green one, right? So is it exactly equivalent to putting its y equal to 0? And if you pay attention, it's x. I mean, this point, this purple one, I don't know, but it is something like -1 and 1. I know that it is not very good, but it is something like this, right? The purple one is -1, 1. So I will just put its 1, which is positive, equal to 0. And the green one, I'm I'm pretty sure that you all know, is that 1. Ooh, where is, what is the undo thing? Okay. Oh. Okay, sorry everybody, but I will make it up fast. So this is the whole thing. This is the area that I want to be in. Yes, everything is okay. The blue one is -1, and then okay, it is okay. This is the point that I have, and then I want to project it, and the projection is going to be here, which is equivalent to putting its y equal to 0. Okay, I don't know who asked the last question, but I want him to come and tell me what is the projection of this one.
Green one or
The new blue one.
the new blue one? Okay, so you would set the +1 to 0, so you have -1, 0. It would be the green
That's
point.
correct.
Or no, I'm sorry.
So,
We're
what?
looking at the one in quadrant 4.
No, I'm talking about this one, which is -1 in y and +1 in x.
Okay, so we would set the x to 0, and it would be 0, -1. Right?
That is correct. That is correct, which is here, and it is 0, -1. Done. And I will do the last one, which is something like here, right? Ooh. Okay, so I guess it should be clear now that the closest point from the red domain is the origin, which is 0, 0. Ooh. Okay, I am going to stop making noise. Okay, clear?
Yeah, so it's just kind of a problem-specific domain
Yes, yes,
issue.
yes.
Okay.
Exactly. So yeah, okay. So let me. Okay, so now I mean I assume that you have this in your homework, and I'm going to talk about it because I think it might be useful. So imagine that you have a circle. So the domain that you want is this circle. So what if I ask you to project this point on the circle? The answer is clearly is that this point is on the circle, so the projection is going to be itself. The second one is that what about this one? How am I going to project this one? Oh, and by the way, assume that this circle has its center on the origin. Okay, what about this? Okay, can someone answer this question? What about this this point, this new point? Where is the projection of this point on the circle?
So it goes straight to the outer edge of the circle. Is that right?
But I mean, outer edge, I mean, I can go to the outer edge this way. I can go this way. I can
Okay.
go this way.
So it'd be
Which
like the
one?
shortest distance.
Okay, okay, I want you to be precise. How can I find, and I will explain. If you don't want answer, I find something. So, okay, let's delete everything. Okay, sorry that I get excited with these things.
That's okay. Sorry that I don't.
No, no, no. Okay, so this is the circle, and this is the origin, and I want to project this point on this circle. Can someone answer this question? I will answer it in a few seconds, but I want you to think a little bit more. How can you find the closest point from this circle to this point? Okay, let's go. This time purple. This is what you're supposed to do. You're supposed to connect that point to the origin, which is, I mean, to the center of the circle. In this case, it is the origin, and then you have to find the projection on this line, which is here. So how can I find the okay, and now assume that this is the unit circle, which has r equal to, oh come on, it has r equal to 1. This is not a special one, this is just a special equality. Okay, yes, okay, so r is equal to 1, and then I want to find this point. How can I find this point? This point has two different, I know two different things about this point. The first thing is that, okay, and let's say that this is point 2 and 1. I had this example before, so we can do this again. Okay, so I know two different things about this projection. The first thing is that it is on this circle. So clearly it is on this circle, which means that it's x square plus its y square is equal to 1. Is it clear why? I think so, because it is on the unit circle. What else do I know about that point? I know that this point is on this purple line, and that purple line is passing origin and to 1. So I guess you all can see that that line is y is equal to x over 2. So these are what these two I know. I know these about this purple point here. So I have a system. I have two variables and I have two equations. So I'm supposed to be able to solve these equations, to solve and get x and y. So I just put these y equal to x here, and then it is x2 over 4. Then I will add this up, so it is 4 plus 1. It is 5 x2 4. So x is going to be 2 over square root of 5. And y, I'm getting better, I think. And y is half of that. It is what? Oh, not now. Okay, it is 1. I want you to know that this is a 1 over 5, over square root of 5. Clear or not?
Yeah, that makes sense. Thank you.
It makes sense. It makes sense. But what is important here is that this is R2. And here R2 was only 1. So if you change this R, then what will you have? You will just have, instead of 1, you will have R2 somewhere here. But where? You will have an R here. Because why? Because then you will have this R2 here, and then you have to get a whole square out of it, and then that R will come out of the square, just like just like how we have 2 here, because we had a 4, right? Do you remember this? We had a 4 here, so then we had y2, so we had x2 over 4, and then that 4 went to the the upper side of the fraction, numerator. I don't know, I cannot pronounce that, but then that 4 comes out of the square root and becomes 2, and then it just exactly just like R. So every time and in every dimension, it is just a two-dimensional question. This is just in 2 dimension. But if it was k dimension, then a projection of a point on a k-dimensional sphere is, and if that circle, I mean, so if assume that circle, that sphere is placed over the origin, it is something like this. It is the point, this is the dimension, this is the coordination of the point, 2 1 over square root of 5, which is the length of this purple line. So 2 over the length of that line, 1 over of that line, times R. I know that I did a horrible job explaining that, but did you understand?
Yeah, I was able to follow that. Thank you.
Okay, awesome. So the question with x, when we want to make sure that x and y are both negative, it is very easy. Just put y equal to 0, or if it is positive, just put anything positive equal to 0. But if, for example, if you want to project something on a circle, then you have to do something like that. And you have exactly this in your homework, which is that hint in, I guess, the third question. Let's go because it is getting late. Actually, no, it's not getting late. So I couldn't manage to implement this one completely, so we didn't get a good result. But I think you all understood what happened in the projected gradient descent. All right, let's go with the Frank Wolfe algorithm.
We can still see the whiteboard that we're working.
Oh. How come? So you're still seeing this one? This thing?
Yes.
I'm going to fix that.
Thank you.
But how?
There we go.
What about now?
Yep, now we're good.
Good. All right. So the Frank Wolfe algorithm. Let me copy paste something here to. Okay, I guess you can see what does Frank Wolfe do, but we are not gonna do that right now. We have to concentrate on so that is my bad actually to print it to put it right now. Okay, so this is the function that we want to minimize, and we have this subject to as well. We want x plus y less than 1, and we want both x and y be between 0 and 1. All right, so let's start by implementing the function. Okay, let me first restart everything so that we don't have to. Okay, so I will start by implementing the function, which is x minus 2 plus right. So this is the function, and then what I would like to do is to get its gradient. So can someone tell me what its gradient is? Can someone please?
So the gradient for x. Go ahead.
Oh, sorry. The gradient for x would be x minus 0.25 times, I guess, just 1, right?
Actually, you have to multiply 2 times x
Oh, yeah,
minus 125.
Yeah, you're right. Yeah, just that.
That is better, but we are not there yet.
Oh.
No, I mean, it was almost okay, but not completely. Think about that. I'm asking for gradient. I'm not asking for partial derivatives.
Are you asking for the y part as well?
Of course, I'm asking for the gradient. I mean,
Okay,
I guess
yeah. I was just giving the x part at that point.
Yes.
Okay, so yeah, that's
So,
the x part.
Go.
And
Go.
then
Continue.
Okay.
Complete it.
Okay, and then the y part will be 2 times y minus 0.25.
That is correct.
Cool.
That is correct. So this is x minus 2.5, yes. And then the second one is just y. So f of x y is 2x minus 2.5, and then 2 y minus, please, what is wrong with what? Okay, good to go.
Yep.
All right. Okay. So I'm hearing myself. Now we get to the part that we want to know, what does Frank Wolfe do? Frank Wolfe starts with approximating a function by its Taylor expansion. So, but with the first two terms. The thing is, we don't have to really know about Taylor expansion, but Taylor expansion is something. I mean, this the only thing that I want to tell you is that I guess you all know about, in a convex function. Let's not go there. So it's just, I mean, we approximate a function by its Taylor expansion at a point xt. Okay, I'm in charge. Okay, so we approximate a function by its Taylor expansion, and then we want to find the minimum of a function, just like what we have here. See, we have this function and we want to minimize it. And what Frank Wolfe tells us is to take its Taylor expansion and then minimize that. But the beautiful thing about it is that at this point, this is f of xt is fixed because xt is fixed, and then the gradient of f of xt times f of xt is also fixed because both parts are fixed. So the only thing that is not fixed and the only part that we can minimize is this thing. So we want to do this part. Okay. Any question?
Why is it? Wait, why is it reduced to x again? I'm just a little confused on that.
Yeah. Just think about that. You want to minimize this function. Okay. And okay, this is the gradient step part. Okay. I guess I have to put this one first because it is now confusing. So with long, we no, it's not important what I'm writing it. But okay, so the first thing is that I want to calculate. I mean, this is we are going back to gradient descent, but this time instead of using the gradient itself, we want to utilize S. What is S? S is this thing. S is obtained by minimizing this function. This is the first two terms of the Taylor expansion of f of x of f. If you're asking why does this one, why can we reduce this one to this one? It's because it is a minimization over x. But this one doesn't have any x. It has xt, which is fixed. Xt is fixed at each iteration because you passed xt and then you want to minimize the function. So xt is fixed so as f of xt. Is it clear that xt is not a variable? Oh, that xt here is not a variable. Xt is a constant here, and then f of xt is also a constant. Is it clear? I want to emphasize on that if it's oh, okay. So I mean, I know that x is similar to xt, but x at each iteration, think about that each iteration. At each iteration, you determine xt and then you just pass it to the function. So everything is known about it. You cannot minimize it after having it. So f of xt. What?
Is it just like, minimizing a function plus a constant is, you use the same value for that as you do for minimizing it without the constant?
Exactly. And f of xt here is a constant because xt is fixed. You cannot change it. So f of xt is a constant. Then in this multiplication, the gradient of f of xt is also a constant because f is fixed and xt is fixed. So the gradient of f of xt at that point is fixed. So its multiplication to xt is also fixed. So the gradient of xt transpose times xt is fixed. So okay, let me change it a little bit. To x minus f of xt. Good. Yes. Okay. So what we have here is that, okay, so the first term is fixed. The second term is not because it has x. And the third term is also fixed. So just get rid of them because they are not going to change the minimization problem. So just get rid of them and then find it. Oh, and by the way, we are not minimizing. This is the argument function. So we just want that x. What if we were minimizing exactly the same, but we just wanted to make sure that we add f of xt and this one at the end after we're done with the minimization process, right? But this is just argument and we don't even need to think about them. We just throw them away. So the problem is how to minimize that, right? So question.
So because none of the other variables are dependent on x, we don't really need it, considering the fact that x and t are constants.
At each, that is what you said is exactly correct, but I just want to add at each iteration x of the xt is constant.
Yes, thank you.
Okay, so let's go again with the big picture. So I will import numpy p and then initial point for this one. This is a two-dimensional. Do I have to start from something special? No, so I will start from -1, and then iterations, thousands, it's not important, and then I will x star y star. I hope that I don't have to go back to the other implementation, but I guess we're good. Okay, gradient descent of initial point and iterations, and then I want to print x star y star, right? Just as we did last time, exactly the same. But what about this function? I want to implement it. So we start with def of this one. So it wants initial point and iterations. That's not important for this. Okay. Okay, it's not important. Okay, so now here I will again do the same thing, which is x is equal to initial. Just to make it a little bit better. Make sure. Okay, the initial point is 0. And then y is equal to initial point 1. So and then I will say iteration in range of. Wait a second. No, it's okay. Okay, so okay, I will say iteration in range of 1 to iterations. Then something that we know about Frank Wolfe is that we have to implement our step size. What is that word for it?
Definition?
Yes. Definition. Yes. Thank you. So we have to have gamma like this, and then I want to use something to give me x and to give me the s. And what do we want to calculate s? Can someone tell me? I just I mean, S is the argument of this one. So the only thing that I want to calculate ST is XT. So I will pass NP dot array. I think it was confusing what I just said, but can you please tell me, was it confusing, or you just got what I said? That for calculating, okay, I'm not, okay. Let me one more time separate this part and bring it here so that you all can see it. I'm going to do this. This is the update for Frank Wolfe algorithm. What was the update for a normal gradient descent? It was gamma times the gradient of the function. But here the update is like that. So the whole, okay, so let me just change this one as Frank Wolfe, so it's better. Frank Wolfe. So the Frank Wolfe algorithm has this update. So I want to have iterations, and I want to do this thing at each iteration. So what I want a gamma, I want S, and I want xt. Xt is okay because xt is x and y at each iteration. So then I will have x is equal to x plus gamma times st0 minus x, and then I will have y equal to y plus gamma times st1 minus y. I think it should be clear, but please let me know if it is not. Do you have any question? It's really clear, or you're just not asking questions? Because I don't think that I did a good job.
It seems clear enough for me, but
that makes perfect sense to me.
Good. So so okay, if it is clear, so tell me, what am I going to do with this get S?
you get the argument of the gradient times x, transpose x.
That is correct. That's correct. So let's come here and let's define get S with the that is not the best thing to do, so let's just separate them so that we see them later with x and y, right? Okay, I want to use okay, so let's go here and then from SciPy import optimize, if I'm writing it correctly. I think it's okay. Okay, good. So because you have this as well in your homework, so please pay attention. Okay, so let's go here to see what do we have here. Okay, this function, as can you see this page, this new page? Good. So what do we have here? We have C transpose X, and C is constant, times X. So it's a summation of CI XI. So we want to minimize that. and with some subject. And the only thing that we're supposed to do is you just pass A, B, L, and U to linear program line program of this library. What I want you to tell me is that what are the constraints that we have, and I will put it here. I think you can see everything. Okay, can someone please answer my question? Given this problem with x plus y less than 1 and x and y both between 0 and 1, that's it. This is the only thing that you need. These two. Can someone please tell me what am I supposed to do with this thing? I mean, my problem is okay, so here I have gradient of f in xt transpose x, right? So it is clearly c. So my c is very clear. It is the gradient of that. So I will say that c is get gradient at x and y, right? So this is c in this terminology, in these notations. What about the rest? I want someone to help me. Please. I mean, come on, I need one volunteer.
You have two greater than or equal to constraints, but you need to put one of them in standard form first.
We have two, which is almost, yeah, we have two. Let's just talk about this one first. I want all of the x's and all of the y's less than 1, and I mean I want x and y less than 1 and greater than 0.
Right.
So here, how can I put those constraints in this terminology?
It's using the AUB and the BUB.
I don't know if it is possible. It might be, but there's an easier way.
Oh yeah, you can use the L and U. I didn't use those. Okay.
Exactly. I can just use LU. So we come here, L is 0 and U is 1. That's it, right? So we have one more thing to solve. X plus 1 has to be less than 1. Okay, please. X plus 1 less or equal to 1.
All right, so now we use the matrix version.
That's correct. Which one?
I don't remember what the constraint is. If it's a less than or equal to constraint, then we use the AUB.
AUB, good. So yes, it is. It is x plus y less than 1. So I want you to tell me what should be AUB and what should be BUB.
BUB is 1, or a vector with just 1 in it. And
that is correct.
Is the vector 1, 1.
That is correct. But is it the vector or it's a row?
Yeah, a matrix with one row that is 1, 1.
That is correct. That is 100% correct. So I will define AUB equal to numpy 1s 1 2, and then I will define BUB as numpy 1s 1, 1. And it is done. So I will just say that optimize dot line prog of C is equal to C, AUUB equal to AUB, BUB is equal to BUB, U equal to, and bounds equal to U and L. L and U, of course. Just, and I want it to be ANS. Print ANS, print, print ANS dot X, ANS dot X, I think. Okay, I think it should be okay. And we can actually test it. Okay, let's test it. I would like to. What do I like to do? I want to have. Let's just say that x is equal to 1, and then y is equal to -1. Oof. Get sxy. Get gradient is not bad. Okay, let's first. Okay, let's first do that, and then we will come back.
It's just misspelled. Gradient.
No, I haven't defined the function.
Oh, okay.
Because
it's
we are
also misspelled. Grad in it.
Yes, yeah. This, I don't know if it is important for you, but gradient. Is it okay? Yeah, I for all the typos and misspelling, I'm sorry, but I don't. Yeah, I think it's okay. Okay. But the thing is that we are in a new problem, and I just reset everything here, so we don't have that gradient before, which was wrong if we had, because this is a new gradient. This is not the previous one. So and we have the gradient here. So let's implement it here. So def get, if you want me to just do that, yes. And then I will say gradient is equal to mb dot zeros array, which just make everything easy for us. And then the gradient 0 is equal to 2 times x minus 25, and then the gradient 1 is equal to 2 times y minus 25. And then return gradient. So I think this is also okay. And then we have this one, which I will delete, and then get the gradient, and then this thing. This should be okay. And this one. So I think we have everything. So let me just first restart, and then we will from the function. Okay, so the function, and I would like you to check with me to make sure that everything is fine. So the function is not really important, but we have it. Oh, the gradient is 2 times I think it is okay. So let's go and then get s. S is the gradient, which is and it is whoa, okay. See, this is not correct, because the gradient here is a row, and I want C to be a column. Am I right? Yeah, I want C to be a column. So it is not okay. I will do this. Now it's a column. So now that C is a column, then I can pass it. And then A, I guess, is the correct size, which is the row. Then B is also, and we have L and U as a scalar. LU, I think it should be okay. And then we have the Frank Wolfe initial. The gamma is this thing that that one of you said is going down. Then the get S is supposed to go and get the S for us, and then this is a plus, this is a minus. I think everything is okay. So see the cursor. Of course. Okay. Where is it? It is S. What? Return ans.x. Okay, we are seeing something. Okay, this is the result that I'm printing. Okay. Let's just get rid of this one because I just wanted you to see what is the output of line prog. What you can, I guess you can see it. And I will. And 1000 iteration is too much. Okay, is this good? Who knows? Okay, let's not waste any time, and then I will just immediately switch to the one that I implemented before. Good. So no, we don't want this. Okay, so I will restart. Yes, do you see this one, right? I hope you see this one. Okay, so again, the derivative is the same, the gradient is the same, and we have this one. This is the gradient. Again, we get the gradient, and then we just pass everything to this one, and then this thing. Apparently that final answer was not exactly what we wanted it to be, but I guess we will go back after we finish the third problem. We will go back and make sure that we fixed everything, because I just want to make sure that we finish everything before 1 a.m. actually. Okay, so please ask your questions about Frank Wolfe because it is done. As it makes some noise so that I can understand that you're hearing me.
We can hear you, and that's the process. I was able to follow that.
Okay, great. The whole point was, I mean, the function was okay. The gradient, just remember that the gradient is a vector. You have to take the derivative for all of your variables, and you should know which variable you're optimizing with respect to what variable you're optimizing. That is really important, because for example, in your homework, you're optimizing you're optimizing over in one of your questions, you're optimizing over lambda, which is a little bit strange, at least to me, because it is not x, it's not nothing, it's just a lambda, it's just a convex combination, it's just the weight of the convex combination. So you have to find out which variable you are trying to optimize so that you get the gradient based on that with respect to that variable. these questions, these are simple questions, so it's just these problems only have x and y, and you just get the gradient with respect to x and y. But in for example, in your homework, you have x and all of sort of familiar variable, but then suddenly out of nowhere you are supposed to optimize lambda. So you have to be aware of that, and you have to take the gradient based on lambda. And in your again, in your homework, you have two dimensions. One of the dimension, I mean, you have a number of data points, and then you have a dimension, but you're not supposed to get the gradient in your domain. You have to get the gradient based on number of data points that you have, which I find quite confusing. So be aware of them. Be aware of what variable you are getting the gradient with respect to. All right, so and this is the as we mentioned earlier, this is the ST. This is how you should work with. Oh, and this is almost what you have in your homework. The only difference between this one and your homework is that we are in your homework you have quality. Here we have an inequality. So you just change AB with AEQ. If I think it is, yes, it is AEQ. So you're seeing important part, and I will share this collab with you later. But I think you should I mean, you should ask your question if you didn't understand. You should ask a question right now. And the Frank Wolfe, as we mentioned earlier, it is just like a gradient descent, but instead of using the gradient, we should get this S and then use it. And all right. Any question?
Is the lambda thing going to be the next thing that we discuss? Because you said the third one's going to be really similar to what we're doing in our homework.
Yes, this one. This last one. This last one is going to be, I think it is similar, and it is similar actually. Okay. So the last problem. After we finish this one, we go back and see what went wrong in those in those two. But here, okay, and this is also from slides that you're supposed to find the ball of the smallest radius that encloses a collection of points. Okay, can someone please tell me? I mean, if you cannot understand how to do the part B of the third question, can you please tell me what is wrong with that and what is confusing you in that question? It's going to be helpful. Yeah, go.
I'm just confused on like reformatting the equation so that like you can plug back in the actual variable, like, you know, in here, like replace an R with the function, I assume is what we're doing here. Is that right?
Okay, good. Yeah, I mean, I've heard that, for example, one student told me that what is R? What is the derivative of R? R is just something, I mean, it's just a variable. What is the gradient of R based on X and R and everything? What is that? The thing is, which I think is very difficult, it's going to be very difficult for me to explain because it's not very, it is quite, it's both easy and difficult for people to understand that when you're maximum, okay, let's go let's go here. Let's go here, and I will. Okay, so let's just say that I have. Can you see this whiteboard?
Yes.
Okay, so let's just say that I have 2 lines, 1, 2, and the constraint is that the point that you're okay, and the point and this is y, and I want you to give me the max of y. Ooh. When you are bounded to be under these 2 lines. So it's clearly this point, right? It is on the boundary. It is not here, it's not here, it's not here. It is on the boundary, because when you have something like a less than this line, when you have a boundary like that, then you have to go on the boundary to get the maximum thing that you have, to be the maximum possible value. And in this case, it is the intersection of these 2 lines, but not necessarily. For example, if this is a horizontal line, and then this is 1 line, and this is 1 line, and you're bounded to be here, and then they want the maximum, then you have to be on this line. This is, as I said, it is both easy and difficult to understand, that your answer is on the boundary. So what does it mean here? It means that this inequality that you have, for at least one of them, or maybe more, which is usually more, you have the equality, and for the rest it is the inequality. So what should we do? We will just replace it. We can just write R
Still see the whiteboard.
No. Good?
Good.
Okay. So, just say that I want to, and in your question, in your homework, you also have that thing, that there's something getting rid of y in your homework, if you remember. So here, I want to just get rid of r, just as you are supposed to get rid of y in your homework. So how can I get rid of and I'm giving you this hint: r is equal to the maximum of something. What is that something? I'm doing I know that I'm doing a bad job explaining it, so this is the reason that I'm going to emphasize more on your collaboration to make sure that we're all understanding.
R is the maximum of the xj minus x thing. I forgot what was the word.
What do you mean? Do you mean the norm, that the second norm, the L2 norm?
Yeah, the second norm. I forget the word. Sorry.
Yeah. So, what is this maximum iterate? What does this maximum iterate on? I mean, what under this maximum? You see what I'm saying? This is the maximum. Maximum is supposed to go through something, and maximum. What is that something? Come on. Who answered that?
I'm not sure.
No. You said something right. I guess my question is quite bad because apparently you're confused, because what you said at the beginning was okay. I just wanted you to be more precise about it.
It's not a question. It's conceptually kind of difficult for me.
Yeah, me too. I'm just trying.
Is it
So
over
what
the
you okay?
point?
What?
Is it over the points from like 1 to big M or whatever?
That is correct, but from 1 to what?
Big N, the number of points, I guess.
Yeah, capital M. Yes. And I will explain why. As you said, that maybe a little bit conceptually. I will explain in a second. So, I think this should be do it. Yes, and I would like to also make it easier by replacing the L2 norm with a summation. Okay. So the thing is that imagine that you have a few points on the board, as I hope you see. You have this one, this one, this one, this one, and then this one, right? And I will tell you that the point that I want you to put your circle on, I mean, that I want to be the center of the circle is here. So can someone please tell me what is the radius of the circle that will cover all these black points with the center of the red one? Can someone please tell me what is the radius?
It will be furthest away from the original point.
That is correct, which is this one, right? This should be this one, because this is, yeah, this one. So we know the circle. So knowing x is equivalent to knowing the radius. Let's just go with another one. Let's just say that I'm here. Let's just say that I give you this one. Again, knowing the center, knowing x gives you the radius. There's no doubt about it. So r and x are dependent, and knowing x 100% gives you the r. And what is r? You find the distance here, 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 and there, and then get the maximum of it, which is this one, and this is your r. Did you understand or not?
Yes.
Okay, one more time. I'm putting this one here. So for the first data point, this is the distance. For the second data point, this is the distance. For the third one, ooh, that's a distance. Okay, for the fourth one, and for the fifth one. And I will find the maximum, which I assume that this is, although it is quite curvy, but I think this should be the largest one. So this should be my R. Can you see? I guess you cannot see it, right? You cannot see the collab, right now.
We can't see the collab, no. It's the whiteboard.
I don't know what is wrong with this. What about now?
Now we're good.
So what did we do? We go through all the data points, j from 1 to m. We calculated all the distances and then return the maximum as r. Clear?
Yeah, that's clear. Thank you.
That's clear. What you have in your homework is the other way. You have a maximization problem, but then you have to do a minimization inside. And those two things, I don't completely remember the question, but what I remember is that when you have everything, then the y is determined. So it is exactly the same. So you have to just put something else. Okay, so let's do this thing as well. So I will define triangular edge. Please. No, it's not. Triangle. Okay, I will define this function so that it makes it easier for me. So we have a new problem, which is the previous problem. So we want to minimize over x only in of g of x. Okay, is this our problem or not?
Yeah.
It is, right? So okay. So what am I going to do? Can someone please give me a few seconds rest and tell me what am I going to do next? What I am going to do next?
Take the get the gradient, which is like the partial derivative with respect to x.
That's correct. That is correct. But and what do you think about this g? I mean, is it convex? Is it concave? What do you think about it?
I think it's con.
And why is that?
Well, it's just, isn't it an affine function within like the inside the squared, and I just remember that a squared function is a function that's squared and convex. It's also convex, and since it's a sum of convex functions, it's also convex. And a maximum of convex is convex when the stuff inside is convex.
Sorry. Yes, everything was correct. So it's a maximum of some convex functions, so it is convex. So, and we want to find its minimum. So everything is just perfect. We want to find the minimum of a convex function, which is possible. What you have in your homework, you want to find minimum of a concave function. I'm sorry, maximum of a concave function, which is also possible. So yeah, everything is just, I guess, all right. So, but the derivative is a little bit tricky, because what is the derivative of this thing? I mean, okay. Let me be a little bit more precise with my question. What I want, we have n-dimensional x's. So what we want is to right? We want to know what this thing is so that we can, I don't know if it is necessary for me to do with this, all of this with align or not, but done. Right. This is something that we are about to do. We want to know what is the partial derivative over xi so that we put everything together and build the gradient vector, right? So how can I calculate the partial derivative of gx over xi? Can someone please tell me? And I will go back to the whiteboard to show what is happening. Okay, let's go to the whiteboard. Okay, the maximum function is something like this. You have you don't have lines over there, but I guess we're fine. So you have a couple of lines. To be precise, you have capital M number of lines, and then the function is the maximum of them. So the real function, if you want to go, if you want to see at this point, if let's do it pointwise. So here the maximum is this one until you get here, and then the maximum will be this line, and then the maximum will be this line, and then the maximum will be this line. So this is your function, right? So what if I ask you about the derivative at, okay, wait a second. And this is this thing, this one. Of course, I'm pretty sure that you all know that this is a two-dimensional question. We have more than that, but it's just okay. So what if I ask you to give me the derivative at this x? Can someone please tell me what is the derivative of this x? Hello?
Looks like -1.
-1 is good, but let's just say that this line is minus x plus 5. The minus was okay, but since we didn't have any equation for the line, the -1 was a little bit, but I guess the answer was good. The point here is that you have to find the line that is maximum at x. You have to find the line that determines the value of your function at x, and then take that line's derivative. So here, if I draw those lines, and this is going to minus infinity, don't care about that. So at this point, this is quite low. This is here, and this one is the maximum. So I will find this line and then take its derivative and put its derivative as the derivative of my main function. I guess it should be clear, but please let me know if it's not. And please, someone answer this question. This is x1. This is x2. Okay, what is the derivative of what should be the derivative of my red function at x2? Anyone?
Be around negative 0.2, something like that.
Yeah, I appreciate if you don't assume the slope of this, but it is actually no. Actually, let me correct myself. It's even better. Let's just say that it is minus 1/3 of x plus 2. So it is minus 1/3 because I want you to tell me that you will find the maximum function at this point and then return the derivative of this line. And for the not final, but what? Okay, so what about x3? Oh, and before you answer, I will say that this is 2x plus, actually minus 7, and this line is 2/3 of x minus 3. Okay, can someone tell me the derivative of the red function at x3?
At x3, it looks like it's kind of towing into the 2x territory, so it'll be 2.
Fantastic, that is correct. So this line is the maximum. So okay, for 2 more, 1 is here. So x4. Ooh. What about this? What about x4?
Derivative at x4?
Yes, the derivative of the red at x4.
Anything between negative 1/3 and 2/3.
That is exactly correct, and I want everyone to know this. That I wanted x4 to be just under this point, so that we have two lines with equal value at x4, so that we don't know which one. Is this line or it is the other line? It is both, so the function is not differentiable at x4, so you have to use subgradient instead of gradient. So anything, as you said, anything between minus 1/3 and 2/3, anything between, let's just say 1/3, anything in between. And for the last one, x5.
So it'd be the same sort of deal, something between -1 and -1/3.
Fantastic. Yes. We're good. All right, so going back to the, I think it is going to work this time. Is it working? Do you see this?
Yeah, we see it.
Okay, good. So the process was first finding the maximum and then returning its gradient. So I want to find the maximum first. Which line, which function, in which j, this is better, which j, I will name it j star, which j gives me the maximum value. So it should be something like argmax over j of that sum. Uh, what about that? Good. How is it? What does J represent?
J is representing the x value that maximizes the function at each point. Is that right?
Oh, okay. It is my bad. Actually, it's my bad. It's my bad that it is confusing. Okay, so let's do something else. Okay, at each iteration, you have xt, just like any gradient descent. So you have one x, and then you are supposed to update that x. We name that x xt because it is at the iteration t. So what we are going to do, as you saw earlier, when we were talking about x1, we were going to find which line giving us the maximum value at x1. At x5, each line is giving which line is giving us the maximum value at x5. So it's not just any x, it is xt, because I'm doing it at each iteration, and at each iteration I have to do this thing. So at each iteration, when I want to, so let me change this one as well. So let me just change this thing as well. Right? So at each iteration, I take the gradient at the point xt with respect to x. And how can I get the gradient at that point? I fix xt, and then I will find the j star. So what is j star? What does j star represent? J star represent the j, the data point that is furthest. If it is a word, please, if it's not a word, please correct me, that is furthest from xt. Or let me remind you of what we are trying to do here. We are trying to find the smallest radius circle that covers everything, right? So xj is that point which is furthest from xt. xt is the center of the circle that we are updating at each time. So if you're confused, what is xj? What is xt? Xt is the point that we are updating. Maybe we should maybe it was a better idea for me to name it c. Actually, we can change it right now, so let's change it so that it makes to be clear. So C, but it is a little, it's slightly different with what you see in this slide, because a slide has a C here, but I have radius is the center. So I want to find the center, and of course center is in the same domain. So I have center and I have center here. So if I have the center the radius, as I pretty sure you can also, you already know, so that so that it is less confusing, too many x's, right? Isn't it better?
It's a little bit clearer for me, at least.
Yeah, I think so. I think it should be clear. It should be better. So center, we are trying to find the center. We don't care about radius because having the center means having the radius. So J, what is J is the x. Now I can say it easily. J is the x that is further, that if it's a word, congratulate me, from C. Okay?
Okay.
Good. So now it's time for getting the gradient. And it is quite similar to what you have in your homework. So don't think that you're wasting your time, because it's very similar to what you have in your homework. Okay, now please help me to get the gradient at CT. Anyone? Gradient, anyone? It should be easy, right? Find the function and then get its gradient. Which function? J, as you have the point, you get the x, you get the furthest x, and then technically it's like that. You find the furthest x and then walk towards it. So xj, I mean, as we mentioned, j star point. So among all of them, you just throw everything away, you just throw them out, and then just focus on j star. So the gradient of g, oh, I forgot to change this one, and one more. No, that's this thing. Okay. So the gradient is, I will write it and then I will ask you to explain it for me. No, I cannot write it because I will do it. See, not everything perfect. Okay, can someone please tell me why this is like that? Why this is this? Which is not, which is, okay, it is good. Can someone please correct this one because it is wrong? Can someone please correct it?
There should be a negative sign.
Right, good. But yeah, very good. But can you please tell us why it is like that?
Like doing the chain rule, the squared comes down to be a coefficient.
No. If you haven't paid attention, I mean, I don't know. But this is J star. How can I? But this is J star. Let me do this. Dun. This is J star. This is not J. This is J star. I used J star to get the gradient. This is what I wanted you to notice. And I want you to notice that we find which J gives us the maximum here, because G is this one, right? This is a maximum function. So you have to find which summation gives us the maximum value. And then we have to take the gradient of that summation, not all of them, just one of them, in the case that it is differentiable. And we will get to the point that it is not differentiable. So I will explain more, but I want some of you to try to explain what happened here. Okay, G, as I will try to say, okay, G, let's go back. Very quick. G is the maximum of these functions. So G is this function, right? So every time that I want to get its gradient, I have to find a maximum. I'm just repeating everything. So as we meant, it's actually okay, but okay. So at this point, I have to find which line to get the gradient and then report the gradient here. So this is what we're really doing. That I look at G. G is the maximum of an capital M number of elements. I find the maximum element. Which element is determining G's value at CT? Right? Which element is determining G's value at CT, and then get the derivative of that element. Right? So imagine, so for J star, it is the summation over I from 1 to n of xij star minus CIT square, and then I have to take the derivative of that thing. So it's a summation. Let me write that. So it's a what I want to do. Okay. So it's just the summation of J star, and now I want to get the gradient. Right? After I find J star, then I know that I know that G of CT is this value, right? This is okay. I guess it should be clear now that G of CT is this value because it is the maximum, right? G is the maximum, so I find the maximum here. So G in CT is this much, right? So then I want to get the can someone please make some noise so that I can say that I'm still online?
Yeah, we're still seeing and hearing.
Great, thank you. Oh. Horrible. Okay. So g at CT is this much. So the derivative. Oh, come on. Okay, now it's okay. Okay, so the derivative of g at CT, the derivative with respect to xi is supposed to be the derivative of that thing, right? And its derivative is this thing. I think it should be clear. How about that? Which part don't you understand?
I don't understand why you got rid of the summation exactly.
Which summation?
The most recent summation where
You're saying
yeah.
that y after getting the derivative, there is no summation anymore?
Yeah.
Oh, okay, good question. Oh, listen, we are getting the derivative with respect to xi. Okay, good. Now I can do something. Uh, 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 I guess you're all tired and everything, but yeah, this is what we can do. uh, so let me just get rid of this one as well, and then put an end here. Whoa. Oh, good to go. Okay. So as you see, the summation is this thing, right? Oh, I hate everything. Now we're good. Okay, the summation is this one, right? So if I want to get the derivative with respect to x1, for example, this doesn't, c1, sorry, c1. So this is all my bad. That why don't I have, why am I getting the partial derivative? What is it? Partial c. Good. Okay, so this one, okay, so let's just say that we are getting the partial derivative with respect to c1. This one doesn't have c1. None of these has c1. Cn doesn't have c1. So we have to just put them in trash and then come here and then get the derivative of this first element, which is minus 2 x1 j star minus c1t, which is this one. So again, when we are getting the derivative with respect to c2, c1 is not c2, so just throw it out. Cn is not c2, so throw it out. So the only thing that we have is this second term, and the derivative of this second term is 2 times x2 j star minus c2 times the derivative of this one, which is minus 1. Clear or not?
Yeah, it's more clear now.
Is it? Good. So I think okay, can someone please answer this question, that what about subgradient? I mean, I'm putting j star equal to argmax. Is it unique always, or it's not unique? We already discussed that. Can someone please try to explain something about, I mean, to say that, is this okay to do the gradient thing this way, or it's not okay?
I think it should be okay to still do it that way, because even if we're at one of those points where it's not actually differentiable, we're still taking just the pointwise maximum. So if we got the line, let's say on the left or the right in the two-dimensional case, it wouldn't matter which one we used. It would still be okay. Which gradient we used.
Yeah, I agree. It should be okay, but just in case that, but we have to, but I have to emphasize on that J star is not necessarily one J. It might be multiple J's. So you have to get the gradient out of all of them, all the J stars, and then you should find, for example, a combination of all of those gradients. So it is important that J star is not necessarily one J, it might be multiple. You have to get the gradient of all of them, just exactly as we are doing here. You have to get the gradient of all of them, and then get a combination of all those gradients, which can be anything, any of them. And of course, yeah, one of them is one of them. I mean, one of them is a combination. So I think don't we only we let me just do this thing, and I need to actually go for a few seconds, and I think it is both good for all of us to have at least a few second rest, and I will come back in like a minute or something, and I guess you should see this one, and I'm coming back in a minute. You just take a deep breath and try to understand what is going on. Where is Zoom? Where do you think Zoom is? Actual size. And think about all of your possible questions. I'm coming back. Okay. Question. Any question? Hello.
From me.
Good.
Okay.
Good. Very good. Uh so which let's start with the main function. So again, initial point. Oh, wait a second. Wait a second. So again, import. There's a question somewhere. I had to miss the last bit of this, but I have got. Don't. I guess. Oh, it's all right. It's all right. I think that I'm recording this one, and I don't know how I'm going to share this, but this is being recorded. So yeah, no worries. Okay. Okay, good. The initial point is okay. So let's just, and for this one we go with 2 dimension again, but I guess you get the idea that it doesn't have to be 2 dimension. It can be anything, but I guess I prefer to have some result that you can see at the end. So yeah, so we start from 1 1. The initial point iterations is let's just say 1000, and then I want to apply a gradient descent from the initial point and the iterations, and then I want to get the C1, C2 from this, and then okay, and we need the data, so I will just do this array okay, 4 is enough, I think. Okay, the first one, let's just put 0 5 and then 0 -1 and then 0 -2 and then 1 0. It's easy, so that we can all, so we see where it should be the center of this thing. Okay, so this is the data, and C1 C2 print C1 C2. I think we're good to go. Okay, so I want to implement the gradient just all the thing that we did. The gradient descent, I wish I had those as well. Okay, so for now I have x this time I will say x1 is equal to initial point 0, x2 initial point 1, only 1 is enough. Okay, then for iteration in range 1 to iterations. Okay, so what do we need? We need to get gradient of x1 and x2. Let's fix gamma right here. What is going on? Let's fix gamma right here. What is happening? Okay, gamma is, again, let's just go with that thing that I can say. Now we get the gradient as gradient. And what am I supposed to do here? I'm just supposed to say that x1 is equal to x1 minus gamma times gradient 0, and then x2 is equal to x2 minus gamma times gradient 1, and then return gradient. So return np dot array x1 x2. Okay. Any problem so far? Any questions so far? Okay, I think it should be okay because everything is just, I mean, we saw everything again. The start, I like to start from the main function and then gradually add details to it, which always going wrong, always goes wrong, but okay, so def get gradient x1 x2. Now what I want, this is the exciting part of this. Okay, so the gradient I will define arg max func. What is that? Arg max func of x1 x2, because arg max only needs, oh no, okay, c1 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 c2 c1 c1. Do you understand what I'm saying? I'm just putting this one equal to c for you to be more clear. C, J star, and then what we want to do, we want to say that the gradient is p dot array of 0, 0, just to initial everything. Gradient, please forgive me, is equal gradient 0. Any question?
Wouldn't it be C1 and X1, not C1
Wait,
X C2? Where you said C1 and C2, but wouldn't it be C1 X1 or yeah?
for the input argument of the argmax?
Yeah, for the inputs.
I'm assuming that we have, I mean, this is the data, right? So
Yeah.
okay, I will name it X. I will name it X instead of data. I will name it X. And then I think that I will have X here. I mean, after I added this thing as def arg max func, I assume that I have X here. So I don't have to pass X. So I have all the x's, and the only thing that this thing needs is c. As you can see, it has x and it has c, and I think that I mean, me defining x here is enough for me to have x in this function. Is this clear? I understood your question like the argmax needs both x and c, but my answer was that x is shared. I guess just like c is also shared, but I want to pass c for you to see what is happening. So I am using x from there, and then I'm just passing c to it.
I'm still confused why you're passing 2 C's to it, not just one.
You want a c? Okay. Did you see that we have a 2-dimension? We're doing it in a 2-dimension world. So we have a 2-dimension. Every point has 2-dimension. So and just like C is supposed to have 2 dimensions, C1 and C2, just like XY. I mean, I didn't want to name it X1. So C is the X value of the center, and C2 is the Y value of the center.
I see.
Okay. I mean, C is in the same domain as X. It's just another point with a different name. Okay. Okay, let's continue. C1, C2, and then the argmax. Okay. Okay, I guess I have to implement a 4 here. Okay, so let me define this one. If we define capital 4 as 4 or as x dot shape 0, I think, yes, 4. So I will say that for j in range m, which means all of my data points, if okay, I will define a max as 0 if max is less than g of c1 c2, which is wrong. I need to say x of j. Oh, please. Okay, I want to get the distance. Okay, so I guess it should let me go and just copy paste something for all of us. I will explain it, but yeah, let's just boom. Okay, so I am assuming that okay, so I will start with that. I want to make sure that I'm getting all the JS stars, not just one. So every time I am using this norm, which is this summation here. So please don't be confused, but I am saying that data, which is not data, which is x. Okay, and so m and oh god, you know, it's let's not do that. Let's just delete it and implement it like a man. Okay. Okay, for j in range m. If max is less than what? And x of j of 0 minus c1 square plus xj of 1 minus c2 squared, then max is equal to that, and j star is equal to j. And if whoa, wait a second. And if max is equal to that, then j star dot append j, and then return j star. Is it correct? Can someone please tell me that if it's correct or not, or what is wrong with it?
Just the last line has a typo, but besides that, I think it's correct.
Yeah, that is okay. Good, thank you. Yes, yeah, I will. Yeah, this will bring everything that I want. And so I have my argmax. I have the gradient. What? Wait a second. Where is the? Okay, where is the gradient? Okay. Okay. Now that we have J star, I'm lazy and I will just go with the first one. But you get the idea that this is the subgradient problem. You have to get all of them. But let's be quick about it. So I would like to wait a second. Wait a second. Okay, so this is this one, this is this one, and now we are about to calculate the gradient, and this z minus 2 times x of j star x of j star 0 minus c1, and then the gradient 1 is equal to minus 2 times x of j star 1 minus c2. And I think it should be okay, but from the previous experience, it is not. Okay, so is it good for the gradient? And it's just 2 dimension. It's just 2 dimension. Just remember. Let me for j in range for I in range n, and I will put n here equal to 2 for I in range n. Then the gradient n is equal to that, and then I will put the gradient as zeros 1n. Okay, what about this? How about this? Is it good? But just remember that this is not the best thing. We need to do subgradients. But for now, okay. Any comment or a noise? Hello?
Yeah, we're still here.
Good.
Oh wait, quickly, where did you get n from again?
Oh, n is the dimension. Sorry for that, but n is the dimension. Maybe I should just the dimension of the world. It's 2 dimension. If you want to go with something else, you can. But
Okay.
right. I just wanted to emphasize that this should be this is a general case. This is not just 2. This is not for 2 dimension. But I guess we want to see the result at the end and to make sure that the result is okay. So we go with the 2 dimension to see how it's going. So n is the dimension. And here, all of this should be, I'm not supposed to have xc1, c2, but since this is 2 dimension, it is easier to go c1, c2 instead of having a c. You get the idea. So good to go. Let's see the first error. Fear. Boom. Iteration is not defined. Very good. Yes, because it is iterations. Okay. gradient in the index 2 is out of bound. Why? I hate it. I hate everything.
Also misspelled gradient in the return statement.
Here? Yes.
Yeah.
Yes. What about now? Oh, it's still wrong. You're about to you're about to go and see. It looks fine, but what is wrong? Okay. Let's go to the other one. Or you. Yeah, let's go to other one because it's almost midnight. What am I doing? I'm here. Okay, so the argmax here used norm, which I hope you don't mind. But it is just a norm. But in norm, you don't give inputs. You just you should just say that data and did. Yes, I mean, please cope with me with all of these different notations and everything. I will send you an email with the good Google Colab with all the notations that you saw later. But yeah, for now, I hope that you don't mind all of this stuff. Okay, so let's restart. Then do we have something here? No, we don't. So this is the argmax function that we talked about. That its job is to just get all the j's, j stars. This is okay. This is the gradient descent, just iteration, the gamma, and everything. And whoa, as you could expect. Where am I? Okay, it is the gradient temp is 0. What? Okay, let's just change all the data to x as well, so that we don't have to. It's better. It's more similar. It was working last night, I promise you. Ooh. What is it? Where is it at? I'm quite confused. Uh-huh. Yeah, horrible mistake. Fantastico. Okay. What do we have here? Okay, can someone please check? I mean, these are the points that we have. We have 0, 1, 0, -1, 0, 2, 5, 0. Can someone please tell me where should be the center of this smallest circle? Hello. Any volunteer?
I understand that if the center were 0, 0, the radius would be 5, but I don't know how to find the center.
Okay. Okay, let me delete this one. Okay, we have 3 points: 0, 1, 0, 1, 0, -1, and 0, -2. Where should be the center of the circle? Where should be the center of the smallest circle that covers all 3 points? It should be easy. Please try. I mean, I will.
Is it 0 and -0.5?
And that is correct. But why is that?
I just got the 2 farthest points and divide them by 2.
Fantastic.
I got
yes,
the difference divided by 2. Yeah.
Exactly correct. So I just wanted to mention that this answer is okay. So but the answer was quite actually smart, let's say. Yeah, because you didn't do the hustle and get the answer, so it was quite smart. So okay, let's go back to the here. Okay, now we have missing. Whoa, I have 1, 0. I have 0, 1, 0, -1, and let's just say that 1, 2 here. Okay, so it is 0, 2. It is oh, sorry. It is 2, 0. It is 0, 1, and it is 0, -1. Oh, and it is 0, -2. So can someone please tell me where should be the center of the circle that covers everything? It's easy. Hello.
0, 0 with radius 2.
0, 0 with radius 2 does the job.
Oh,
but it's not the smallest. So imagine that if I move it this direction, right? So for example, let's just put it here in -1, -1, in 1, -1. So the distance here is smaller, here is smaller, is the same, but this is larger, right?
Yeah.
I guess, I mean, do you want me to, because no, the only thing that I wanted, that I'm here trying to do is to show you that the answer is correct and how that we reach the correct answer. But I guess you get the idea, right? I guess you don't have to, I mean, we don't have to do that. So let me go to this thing, and then, so if let's just say that if I put 2, then the answer should be minus 0.5 and minus 0.5. Does it make sense?
Yes.
Good. So I think we are done here. I will email you with the link of with the link of this Colab in a few hours, so that you can just go through everything for yourself. And I guess this is, I guess when I stop recording, then it will ask me to upload it somewhere. Then I will do that. And you can always, so, okay, let's not finish yet. Any question? No question, which I don't know. I hope that it's a good sign. But I think my main point here is that it's better to break the problem into smaller problems and then solve them one by one. The whole homework is not that difficult, honestly, but it is not easy to understand what to do. If you know what you're supposed to do, then it is easy to do. But getting there is not easy, I can say. So I think this thing, I mean, I think we saw 2 important things. The first one is that I was trying to code top down. First go with the main function and then just do everything separately and know the variable that you are going to optimize and this stuff. And then the second one is that don't be afraid of a strange thing like that. Just calculate one thing and then put everything together like this, like what we did here. We calculated, is this the version that we did together? No, this is not. Which I guess we are, yeah, this is the version. Okay, so yeah, we calculated R and then put we formulated R and then put out R back to the problem and then we just change it and that's it. So any question?
Are you gonna share this document to us? Or
Yes.
Are you sharing
I
us the one that you finished previously that works completely fine, or the one we worked on today?
I will try to make sure that I will share you this one that we did together, but I will fix the problems.
Okay, thank you. And also, can I ask a question about the homework?
Sure. It'd be about the second one or the first one?
It's about the third problem, the homework assignment, the one
Okay.
where we basically the last question. So you want us to cancel out both constraints in the homework, right?
Let me.
Or do you just want to just cancel out the y constraint?
No, wait a second. I have to open the question because I don't know it exactly. So, okay, we're talking about question 3. I assume.
Problem 3, question 2, part, I think it's B, where it talks about, yeah.
Okay, so what are you saying? What is your question?
Well, I know we have to eliminate the y constraint for sure, but are we also eliminating the w constraint?
What does that mean? I mean,
Like,
I can answer your question, but I would like you to expand the idea of
oh,
eliminating.
I was like, we were eliminating constraints and one of which problem was it? Where I think this one where we were just canceling out the constraints or whatever, like plugging in the how we plugged in the maximum kind of instead of having the inequality. And like since we have two inequalities, do we do both of them? We have two inequalities, but I assume we only have to do one of them. Do we actually do both inequalities?
Uh, we don't. What are you saying about two? I mean, two inequalities. Where is the second one?
Oh,
You
it's
mean
in
no, you mean the W, the second norm of W,
hmm
the square of W is less than gamma. You mean that?
yeah.
Oh, no, that is the projection part.
Okay, just making
No,
sure.
no, no. It doesn't have anything to do with that. Okay, so the thing is that you're just supposed to, first thing first, you're supposed to eliminate y, and we
Yeah.
saw how to eliminate y because
hmm
we in the problem we eliminated r. So
Yeah.
here you just have to eliminate y, and
Okay.
then you have a problem, and then you will have a new problem, like it should be a maximum of minimum of something, right?
hmm
And then if you want to solve that problem, then there are, I mean, for special cases, which is not quite a special almost every time, the problem is not unbounded, which means that W can goes to infinity. I mean, the W is a vector, and if any entry of that vector goes to infinity, then it's not an answer. And then, as we saw in the first problem of today, this is a projection. So at each iteration, you calculate the correct gradient, and then you update your W, because this is a problem that you need to keep the W. You are not going to eliminate W. You have to keep it because this is your variable that you're optimizing based on, right?
So,
So,
so
so yeah, wait, just one more second so that I can finish. So you eliminate y, you put a function with the input argument of w instead of y, and then at each iteration you get the gradient of that function multiplied to the to your step, and then update w. And if that new w is not inside that circle, and I guess you already know that the square of L2 norm less than gamma 2 is a circle, right? So if that W is not in that circle, then you have to project it. And I don't know if you were here at that time or not, but we show how you can uh, project a point in a circle, over a circle, right?
I
So,
saw.
right?
Yeah, I understand now.
Let me go back here. Let me go back here. So this is what you have. No, not here. Let me do this thing. Wait a second. Wait a second. Okay, here. Okay, do you remember this one? So we update x and y, and then project, right? This is exactly your code. But it is not two dimension. That's the difference. So you update your point, and then add a function project, and then in that function project that point over that circle. Am I clear? The gradient, we saw gradient, you have to do that argmax thing for that.
Yeah, and the projection is the W and the gamma thing, right?
Correct.
Okay.
Correct.
Yeah.
You have to project W into that circle.
Yeah, and we have to find wherever the radius, the closest like place to project in is.
Yes, radius for that problem that we saw, and here it's something else. I don't know what it is.
Okay. All right. Thank you then.
All right. So, question. Oh, everybody left. Yo, so okay, this is only 3 of you. All right. So,
And when will the recording will be available immediately after, right? Or did you already stop recording?
no, I am stopping recording